have out just a pencil, we're going to work on practice exercise 55. You won't need a calculator for this. You've been missing algebra class. Here we go. Mini word problems. Just the real short little ones, but a little collection of these to give you a little algebra practice where you'll represent the unknown as x, or perhaps unknowns, one as x, other in terms of x, and solving. So, good review for us. Exercise 55. And we'll wait to get started until everyone has their booklet. Resident Eskimo hands the book back.
55.
All right, exercise 55. You will need two things. First, you'll need an equation. Second, you'll need the answer or answers. Okay, so whoever's first, when I call on, you're going to ask, okay, what was your equation? What was your answer? Or what was your equation? What were your answers? Make sense? So both parts needed, just like we would have done in algebra class. Fond memories. You may begin.
I don't, it's a tick. From one of
He
my
doesn't use them.
It's a tick from one of my medicines.
Well, scratch it with the tissue then.
It's not gonna work. Okay.
let's go and take a look at these together and see how we did. And Quentin was first. Quentin, how did you represent 4 times a certain number is 92? 4x equals 92. Good. 4x equals 92. What was the number? 23. Very good. Next one. 7 times a certain number is 266. How did you represent it? 7x equals 266. Right. 7x equals 266, and the number was? 38. The sum of a certain number in 15 is 41. How did you represent it? Good. X plus 15 equals 41, and the number was? 26. For this one, separate the number 24 into 2 parts so that one number is twice the other number. What was your equation? Good. X plus 2x, those are your 2 numbers, x and 2x, equals 24. If you add parts, you get the whole, right? The whole equals the sum of its parts. So what were your 2 numbers? So what should the 2 numbers have been? 8 and 16 should have been the 2 numbers.
I had it all right.
Because there were, let me ask you, on the last problem, did you give 2 answers or only 1?
I did give 2 on that.
You did give 2 on the last one. I'll stay with you. All right, if 5 times a number is decreased by 12, the result is 108. What's the number? What was your equation?
5x minus 12 equals 108.
Good. 5x minus 12 equals 108, and the number? 24. 3 less than 3 times a number is 45. What's the number? What's the equation?
3x minus 3 equals 45.
Good. 3x minus 3 equals 45, and the number was?
16.
Lynn is 4 years younger than her sister Toby. The sum of their ages is 18. How old are Lynn and Toby? What was your equation? Good. X plus x minus 4 equals 18, or 2x minus 4 equals 18 would have worked as well. And how old is Lynn?
27.
And Toby?
11.
I'll give it to you. All right. Anyone else get them all correct? All right. Chris was right behind him. Good. Jamie also. Anyone else get all the ones you did correct, even if you didn't finish all of them? All right. So, are there any questions on these? It's been a while since we've done word problems much, right? We've done a few, I guess, here and there, but questions? Genesis? Yeah, so for the last one, we should have identified 2 unknowns, right? Lynn and Toby, spelled very strangely. And it said that Lynn is 4 years younger than Toby. So I would represent Toby as x, since that's who it comes back to. And since Lynn is 4 years younger, x minus 4. Did you have that initial setup? And then it says the sum of their ages. So I would add the x minus 4 plus the x. And that equals 18. Again, you'll combine the x's to get 2x minus 4 equals 18. Move the negative 4 over as a positive 4 to get 2x equals 22. And you'll end up with x is 11. Well, since Toby is x, Toby's 11. Since Lynn is x minus 4, or 11 minus 4, Lynn is 7. And yes, sure enough, the sum of their ages is 18. Coming back to you now, wave of fond memories from Algebra 1.
I know how to do it. I just misread my 22 for a 32. So
Ah, okay, that makes sense. All right, any other questions on this?
Can we do like a lot of more word problems?
Maybe some other time. Go ahead and pass those forward if you would, please, and take out your notebooks. Turn to the theorem corollary section. Because for homework last night, you were supposed to copy corollaries 42-1 to 42-3, as well as copying theorem 43. If you'll have that out, so I can come around and check. I'll also turn off the sauna right above my head. Now it's too hot. Yeah, exactly. See, it's extreme. So yeah, you're not right under the heater. So
Perfect.
Getting your notebooks out. I'll be back in just a second. Everyone in the other classes is suffocating. Why did he do this to us? Does he hate us?
Mr. Adasky is like everyone's dad at the school. Like, he's the one that says don't touch the thermometer.
Actually, I've told some of the teachers they can touch it. All right,
Oh, yeah,
good.
like, wait, no.
Good, as long as it's that one on that side of the hall.
He owns this half. Yeah.
My half, don't touch. Whose house? My house. All right, good.
My house, you live by my rules.
Good, and okay, where are the correlates?
Oh, yes, that before you ask, we switched notes so he could look at mine and copy
Alright, let's go ahead and take a look at these here in just a minute. First of all, let's review some terms. It's still blowing on me. Let's go and review some. Stand over here now. Let's review some terms we talked about over the last couple of days. Yesterday, actually, we introduced to you this idea of a line that intersects a circle twice, which if a line hits the circle at all, it would usually touch twice, right? It's pretty special if it just touches once, class, which would be called a tangent. But if a line cuts through a circle at 2 points, we have something called Quentin A. You didn't study last night, did you? Chris? Secant. All right, so a tangent touches at 1 point, secant cuts through at 2 points. Of course, a line could just totally miss the circle as well. We said that to define the length of a tangent, class, you'll take some external point and the point of tangency, and that distances the length. What about the length of a secant, Jamie? Ethan, how do we define the length of a secant? Kendall? Genesis? Audrey? Chris?
Point of intersection. You measure like the first point intersection of a circle and then to the other one. That distance.
Well, that would be a chord, right? That would just be a chord from one point of intersection to the next one. All right, so remember for a secant, we're going to measure from the external point, like we would for a tangent, right? From external point, but not to point of tangency for a tangent line. Okay, that would be length of a tangent. For a secant, it goes from the external point to the second point of intersection. From external point to second point of intersection. We talked about then that a secant is always longer than its own chord because every secant consists of a chord and an external portion. We also said that if you were to find the region of a circle bounded by a chord and its arc, everything inside here is referred to, let's come back to Jamie, as a
minor section.
We don't call it a section, that's the term I'm looking for here.
Segment.
Segment. It's called a segment of a circle. Now Jamie's right, because this is a minor arc, this would be a minor segment. Good. And of course, everything in here, class, would be considered a major segment because it's bounded by a chord and a major arc. We said that any angle that has its vertex on the circle and is formed by two chords is referred to, Genesis, as an inscribed angle. Just as an inscribed polygon has all of its sides as chords and all of its vertices on the circle, so an angle formed by chords with the vertex, singular, on the circle would be an inscribed angle. We also mentioned yesterday that arcs, while you could measure the length of an arc in terms of inches or centimeters or what have you, you can also measure the size of an arc in what unit, Audrey? Degrees. And we said that the measure of an arc will always be exactly equal to the measure of its central angle. Whatever central angle intercepts that arc, that's the size of the arc in the same number of degrees. So if I have two arcs and they are both 50 degrees, Quentin, are the arcs equal?
No.
When would they, when would they not? Okay, go ahead.
If they were in the same circle, they'd be equal.
Right, if they were in the same circle and they're both 50-degree arcs, or if they were in congruent circles and they're both 50-degree arcs, yeah, they're equal. But if they're not in the same circle or congruent circles, no. Just because they're 50-degree arcs really means nothing at all. So that if I wanted to find the measure of an arc, I would just need to know the measure of its central angle. And if I wanted to know the measure of a central angle, I could just look at the measure of its arc. But the inscribed angle, this is where we left off yesterday with Theorem 42, an inscribed angle will not equal the arc it intercepts. Rather, Kendall, an inscribed angle will equal Jamie.
The inscribed?
Yeah, the inscribed angle will equal what? I have a feeling we didn't study, Chris.
Perpendicular bisecting.
Half its arc. An inscribed angle will equal half of its arc. Or you could say the arc equals twice the inscribed angle. So, as we look over at the bulletin board, class, the top two things we have to have memorized by now. Okay? First of all, class, that a central angle equals its arc, and an inscribed angle equals half its arc. We've got to know those things. Let's go ahead and look at the corollaries. You're right there in your theorems corollary section of your notebook. Go ahead and read corollary 42-1 for us, if you would, please, Kendall.
All angles inscribed in the same segment or incongruent segments are equal.
All angles inscribed in the same segment or incongruent segments are equal. Now, inscribed in a circle means that the chords are in the circle and the vertex is on the circle. But if we were to inscribe an angle in the segment, let's just take the top segment here, that means the vertex has to be on the arc of the segment. So the vertex, for instance, here maybe. And that the chords would have to go to the end points. Do we see what it means to have an angle inscribed in a segment? The corollary says all angles inscribed in the same segment or incongruent segments are equal. So here's an angle inscribed in the segment. Here's another angle inscribed in that same segment. The corollary is saying that these two angles have to be equal. Well, question. What kind of angles are these, class, with vertex on the circle formed by chords? Inscribed angle. And we just proven through 3 different methods, in fact, you might recall from yesterday, that an inscribed angle is always equal to half its arc. Let's try that again, class. An inscribed angle is equal to half its arc. All right, so both of those inscribed angles, because they are in the same segment, they are inside this little minor segment here, they both cut off this arc. Correct? And so if they both cut off the same arc, they are both halves of this arc. And if an angle is equal to half of this arc, and this angle is equal to half of this arc, halves of equals are equal. So of course, angles inscribed in the same segment, that means no matter where you put the vertex, all these angles are all going to be equal to each other. Make sense? Because they all intercept the same arc, and they're all halves of the arc that they intercept. Corollary 42-2, put a star next to this one. Corollary 42-2, put a star next to this one. This is an important one to memorize. We memorize most things, but this especially. Make sure you commit this one to memory. Go ahead and read this one for us if you would, Audrey.
An angle inscribed in a segment whose arc is equal to the semicircle is a right angle.
Good. Any angle inscribed in a semicircle is going to be a right angle. Here's the idea behind this one. You have a circle, we have a diameter, therefore we have a semicircle, right? So pick any point in the semicircle and inscribe an angle in that segment. The corollary says it has to be a right angle. Well, question. If we have a diameter, we'd already proven we will have 2 semicircles, correct? Each semicircle is half of the whole circle. How many degrees are in the arc of a circle?
360.
How many degrees are in the arc of a semicircle then? 180 degrees. So that this arc right here must have 180 degrees in it. But this is an inscribed angle, and an inscribed angle equals half its arc. Well, if this is half of the 180, then it must be 90. So no matter where you put your vertex, if you inscribe an angle there, it's a right angle. Right angle. Right angle. Right angle. They're all going to be right angles if they're inscribed in a semicircle. That's something we can use in construction then. If you wanted to construct perpendicular lines, take your compass, make your circle, pretend it's a circle. You see where the indentation is, put any chord through the indentation in the paper. You have a diameter. Pick any random point, connect the dots, you have perpendicular lines. Okay? So you could even use this in construction. Corollary 42-3. Go ahead and read this for me if you would, Ethan.
An angle inscribed in a segment whose arc is greater than a semicircle is an obtuse angle, and angle inscribed in a segment whose arc is greater than a semicircle is an acute angle.
Now, if you take literally what you just said, you contradicted yourself in back-to-back sentences because you have a slight miscopy there. So edit what you wrote. An angle inscribed in a segment whose arc is less than a semicircle is an obtuse angle. The way I would put it, an angle inscribed in a minor segment is an obtuse angle. An angle inscribed in a major segment is an acute angle. That's actually counterintuitive, right? If you were just thinking, you'd be like, okay, major segment, bigger angle, right? Think about it though. If you have a larger segment, and you put an angle in the big segment, if it's in the big, it cuts off small, right? It cuts off that which is less than a semicircle, less than 180. So the angle then is half of less than 180, therefore it is less than 90, therefore it is acute. Whereas if you put an angle in a minor segment, if it's in the minor, it cuts off the major. And therefore it cuts off bigger than 180. It's half of bigger than 180, therefore it is bigger than 90. So obtuse and acute. So if it's in the big, it's small. And if it's in the small, it's big. All right? So an angle inscribed in a major segment class must be acute. Acute. And an angle inscribed in a minor segment must be obtuse. So if it's in the minor segment, obtuse. If it's in the major segment, acute. All right? So that's the way that I will word it. I won't say a segment whose arc is less than a semicircle. We've already defined that as a minor segment. And we've already described major, so I would use those terms, major segment, minor segment. But make sure that you know those. Let's take a look there at page 151 now. So notebooks aside, just have some paper out. If you have a calculator, wouldn't hurt to have it, though I don't know that you need it. The math is not particularly challenging. As I mentioned yesterday, we are going to do a lot more with math, though, in these days ahead. So bringing a calculator to class would be more needful. For the longest time, we never seemed to do any math at all. What's the point of the calculator? But we will do more math. That said, all the math we will do in this class can be done without a calculator fairly easily. So you don't have to have the calculator, but it would be beneficial for many of you, particularly if you never were that great at mental calculation. It's just up to you. I will typically not use one in this class, but again, I am good at mental calculation, so I don't necessarily need it.
I'm a genius.
So you definitely won't need one. All right, let's go ahead and look at page 151, number 1. And Genesis suddenly seems to be in a good mood. She's laughing over there. Maybe she just couldn't help herself. Genesis, go ahead and read number 1 for us, if you would, please.
We're on page 151.
We are on page 151.
In case 1, theorem 42, if angle A equals 40 degrees, how many arc degrees are there in AC? If BC equals 2, AC, find angle A.
Now, notice it says case 1, theorem 42. Look further up on the page. You see where we have a case 1, case 2, case 3? You remember as I was breaking down the proofs of theorem 42 for you yesterday, I showed there's actually 3 different ways you would have to prove it progressively? That's what we're talking about. So they're simply referring to this first picture here. We've got a diameter, AB, and we've got a chord, AC. And it says if angle A is 40 degrees, how many arc degrees are there in arc AC? Do we see how to set up the picture? Well, let's think about this for a minute. What do I know about this angle, class? It is what kind of angle?
Inscribed.
Inscribed. And we know that an inscribed angle is equal to half of its arc. So how big is this arc, class? 80 degrees. But that's not the arc they asked for, is it? They asked for AC, not BC. How would I find AC? Quentin, thoughts? Good. If we have a diameter, that means we also have a semicircle. And a semicircle has 180 degrees. You can do this in your head. You don't need a calculator for this. If you have 180 degrees, 80 of them are here. How many for arc AC? 100 degrees. How many think in the same thing Quentin said? Easy enough. Take a look at the second part now. It says, what if arc BC is twice as big as arc AC? So same picture, but now arc BC is twice as big as AC. Anytime a comparison like this is made, think algebra. Let me say that again. Anytime a comparison like this is made, think algebra. If BC is twice as big as AC, do you notice that BC is defined in terms of AC? It all comes back to AC. Let's let AC be X. And if BC is twice as big, represent BC as 2X. Well, What do I know about x and 2x? Jamie?
X and 2x, that they add up to 180.
They have to add up to 180 because, again, AB, it's case 1 where we have a diameter. AB is a semicircle. So if I know that x plus 2x equals 180, then class, I know that x is equal to 60 degrees. That's this one right here. That means that arc BC must be 120 degrees. But they weren't interested in the arcs. They said find angle A. How would I find angle A? Well, what kind of angle is angle A? Audrey? An inscribed angle. In class, we know that an inscribed angle is equal to half its arc. So therefore, angle A, Chris, must be 60 degrees is correct. How many thinking through the same thought process we went through there? Do you see how to think through these problems? Look at number 2. Read number 2 for us, Ethan.
In case 2, theorem 42, if arc AC equals 84 degrees and arc DC equals 3 arc BD, find angle BAC.
Good, and do you see right there where it says arc DC equals 3 arc BD? We could transliterate it this way. Arc DC is, that's what equals means, 3 times as big as BD. Do you see that? Arc DC is 3 times as big as arc BD. Now notice we're going with the case 2 picture. So on your paper, go and copy that down. Case 2 picture. We have a dotted diameter AD. We have a solid chord AC and a solid chord AB. Start by representing exactly what you know. You know AC is 84 degrees, write down the 84 degrees. But then we come to DC is 3 times as big as BD. What does that statement tell me I need to do, Ethan?
I'm confused.
All right. Chris? Algebra. When you see something represented that way, where this is 3 times as big as that or 10 more than that, use algebra.
Right.
Let me say it again. DC is 3 times as big as BD. So if we're thinking word problems, which we conveniently did as our practice exercise today, which arc should be X, class? BD, because that's what it comes back to. DC is 3 times as big as BD. Let BD be X. How would I then represent DC coming back to Ethan?
2x.
Class 3x. Because it says that DC equals 3 times BD. So if BD is X, then DC is equal to 3x. Are you looking at number 2, Ethan?
Mm-hmm.
Okay. It's 3 times as big, so 3x. Now then, the angle I'm trying to find is, of course, angle BAC. But until I know how big x is and how big 3x is, I can't find this inscribed angle, correct? Because we know an inscribed angle is equal to half its arc. But I don't know how big its arc is yet. But I mentioned it before, I'll say it again. Look for diameters, because where you have a diameter, class, you will have semicircles. And thinking numerically, where you have a semicircle, you have 180 degrees. Where's our semicircle of note here, Audrey? ACD. ABD is worthless to me, because I don't know AB. I know nothing about AB. But I know a lot about ACD. In fact, I know everything I need to know about arc ACD. So I'm only going to look at the top half of the circle, and Audrey will write what equation? Well, I would say that the whole is equal to the sum of all its parts, and let's start there. Well, we're not doing a proof, so we can actually, so arc ACD you said is 180 degrees, right? So don't say arc ACD, say 180 degrees is equal to, there we go. The 180 right here is equal to 84 plus the 3x. And we make a little equation out of it. Do we see what we're doing here? All right, to solve, of course, class, we would need to subtract away the 84. I'm going to subtract 84 from 180, I get 96 degrees equal to 3x. Divide both sides by 3 and x is equal to 32 degrees. Now, interestingly, I actually care more about 3x at the moment, right? Because 3x is right here, and 3x is 96, so I know this is 96 degrees right here. But also that the x here is 32 degrees. The question though was, how big is this whole angle here, CAB? Well, how big is this whole arc right here, class?
128.
128 degrees from C to B is 128 degrees. So how big is the inscribed angle, anyone?
128. Oh no, 64.
64 degrees, because an inscribed angle equals half its arc. Do we see the algebra here? It's less of a geometry problem. It's a geometry concept, but the math involved is algebra. Questions on that? Ethan, does it make sense now that you've seen it work through? It's okay, we're gonna do several of these, okay? So don't sit there feeling lost. It's like, okay, I think I'm starting to get it, and we'll continue to work on these. Let's move on to number 3. Read this one for us if you would, Chris.
In case 3, theorem 42, if C is the center of arc AB and arc DB equals 1/4 of arc BC, find angle BAC.
All right, now there's a little bit of a pause. They perhaps should have used a comma after arc AB. Let me read it again. In case 3, theorem 42, if C is the center of arc AB and arc DB equals 1/4 of arc BC, find angle BAC. Because C can't be the center of two different arcs at the same time.
The center seems to be bad.
Yeah, well, you know, they failed to realize that equation, because an equation is a sentence, right? It's a mathematical sentence, which means we have a compound sentence here, don't we? The and separates a sentence from a mathematical sentence. There should have been a comma coordinating conjunction to separate two complete thoughts. There you go, Mrs. Henderson. All right, so we're looking at case 3. All right, so we've got the dotted diameter here, AD. And we've got this random or not so random chord AB, but it says that C is exactly in the center, or normally class we would use the term, it's the
Median. Midpoint.
midpoint. C is the midpoint. All right, so C is the midpoint of arc AB, which means arc AC and arc BC are equal. Definition of midpoint. Correct?
Yeah, it is. It doesn't not to my eyes. It doesn't look like.
It doesn't matter what it looks like. I did my best. Okay, I'm standing on the side of it. I'm not looking at it head on, so it's probably a little slanted because of my perspective. There's a sermon in there somewhere, but we don't have time. The next thing we see, though, is that arc DB equals or is 1/4 of arc BC, which means we need to use some algebra. What needs to be x, Ethan? BC. Because DB is defined in terms of BC, BC is x. How would I represent DB based on that mathematical sentence that DB is 1/4 of BC?
Me still?
Yes.
1/4.
1/4 x. And there's one more thing we need to label, and it's AC. How would I label AC, class?
Why?
X. How do we know it's going to be x?
I just guessed.
Since they're equal to CD.
Because it's equal to BC, and BC is x, therefore AC must be x. Make sense? Now, if I were to take AC, BC, and BD and put them all together, because I have a diameter here, that must be exactly 180 degrees, semicircle. So therefore my equation should be what here, Genesis?
2x plus 1/4 equals
How many degrees in the semicircle? I couldn't hear you. How many degrees in a semicircle, class?
180.
180. Is that what you said a minute
I
ago?
said 80.
Okay, 180 degrees in the semicircle. Now I look at this, I'm like, oh, fractions. I hate fractions. Let's just get rid of the fractions. Let's multiply everything by
4.
4. And we'll multiply everything by 4. 4 times 2x, 8x. 4 times a fourth x, 1x. Remember the 4 and 4 cancel. 4 times 180.
720.
720. We combine like terms, 8x plus 1x. 9x equals 720. Now remember, this is 72, 0. Divide by 9, we get x is equal to?
80.
You know, that's what Genesis was saying, but she'd already solved it. Alright, so therefore, arc AC class must be how big? 80 degrees. Arc BC must be how big? 80 degrees. Arc DB must be 20.
I have a question.
But what did it ask us to solve for? And then I'll take the question. It asked us to solve for angle BAC. That's this angle here. What kind of angle is BAC? Inscribed angle equals half its arc. How big is its arc? 80. So it must be 40. There you were giving me the answer, right? Just jumping ahead of the answer there. So we have a 40-degree angle. Question, Chris.
With that small of a problem, wouldn't it just be easier to use 0.25 instead of timesing everything by 4?
If you have a calculator, like 2.25 and then divide by 2.25, I don't like dividing decimals. Plus, if you were doing it by hand, now you have to move the decimal twice, and it's 225 divided into 18,000.
I think I had the same problem in summer school because I would always.
I mean, if you're using a calculator, no problem at all. But doing it by hand, stay with the fraction and multiply by the LCD and get rid of the fraction, would be my thought. But it depends on your approach. Okay, questions on that? Let's move to number 4. Go and read this one for us, if you would. Quentin.
Two angles of an inscribed triangle are 50 degrees and 80 degrees. Find the number of degrees in the arc subtended by the three sides.
Read that last part again.
Find the number of degrees in the arc subtended by the three sides.
Alright, so we draw a circle, we inscribe a triangle, and it doesn't have to be perfectly to scale. We already aren't going to trust our eyes. It says that 2 of the angles are 50 and 80. So say that one's 50, say that one's 80. We're not trusting our eyes anyway. We could easily find the remaining angle, could we not? How large is the remaining angle, class?
130.
50. Just remember, the 3 angles together must add up to 180 degrees. So 50 degrees we could find very easily. But it asked us to solve the third angle. It said, find the number of degrees in the arcs subtended by the 3 sides. Well, if we have an 80-degree angle here, class, how big is its arc? 160 degrees. If we have a 50-degree angle, how big is its arc? 100 degrees. Now, even if we hadn't found this to be 50, I could still find this arc to be 100. How? Even if I hadn't found this to be 50, I could still know this is a 100-degree arc. How?
260.
I have 260 degrees here, and how many would be in the whole circle? 360. I'm just missing 100 more degrees, right? So you can use the whole 360, or just find the third angle like we did and say, okay, double it to get your 100 because this is half of 100. Questions on that one? Do you see how to use the math with inscribed angles? Central angles we looked at yesterday, they're even easier because you know the central angle, you know the arc, you know the arc, you know the central angle. Inscribed angles, you just have to remember to half it to get the angle, double it to get the arc. Questions on this? All right, turn the page and let's look at number 6, which is a proof. Number 6, we have a proof. Read this for us if you would. Let's see, who hasn't read yet today? Audrey, I'm getting somebody pointing at you there, not wanting to let you off the hook. Audrey, read number 6 for me.
A circle is circumscribed, triangle ABC and single point RKB. Prove that angle ABM equals half of angle C.
All right, now notice they didn't give us a picture. We're gonna have to come up with this. What's the first thing I should draw, class?
Circle.
A circle. Start with a circle. What should I draw next, class? A triangle inscribed within, right? Because the circle is circumscribed, so the triangle is inscribed. And what should I name my triangle, class?
A, B, Z.
A, B, C. But that's not all I should draw. There's another thing that needs to go in my picture. A midpoint. Specifically the midpoint of arc AB. So find wherever your arc AB is, and to the best of your ability, try to locate the midpoint and name it M. We're going to try to prove, Audrey, say it again, that
Angle ABM equals half of angle C.
angle ABM. I don't have an angle ABM yet, which means in order to get it, in order to prove that, it's assumed this chord BM must be there. Also draw the chord BM. So when we go to write down our given, we're given, let's name our circle, I can't name it A for Audrey. I'm drawing, R would be the middle initial? Yeah. Okay, I was trying to think, what's your middle name? I can't remember. R. So let's say given circle R with inscribed triangle ABC, M is the midpoint of arc AB. We could specify chord BM. I don't know that it's necessary to write that, but it wouldn't hurt to say also chord BM. But we're trying to prove that angle ABM is equal to half of angle C. Once you have that down, 2 columns, statements, reasons.
It's gonna go in your notebook.
No, not necessarily. It can if you want to put in like class notes or something, but not necessary. Anytime it must go in the notebook, I will tell you in advance. All right. I've got your first statement. Circle R with inscribed triangle ABC. M is the midpoint of AB. All right, so this angle gotta be half of that angle. Well, we got one clang in the given class.
Midpoint.
Midpoint. What is a midpoint? Tell me, Chris.
Half. It cuts off half of. Okay. What are you asking? Like
What is a midpoint?
the middle section between 2 points.
It's not a section.
The middle.
It's a
section.
point.
The point between 2. Why am I blanking on this? I know this.
Help him, Ethan. What's a midpoint? You gotta be kidding me, folks.
A point between 2 lines, or?
Quentin? Save the basketball team's reputation here.
The bisector.
What's a midpoint?
A point that bisects
What does bisect mean?
2 equal halves.
Ah, so a point that divides it into 2 equal halves. Oh, okay, good. So if M is a midpoint class, then that means that arc AB must have been divided into 2 equal halves. What are the 2 equal halves? Arc AM and arc BM. So number 2, we should state, back to Chris, that
Arc AM equals arc B.
okay, we could say AM equals BM, or we could say that arc AM and arc BM are, to use the word phrase, equal halves of arc AB. Now, I've mentioned before, midpoint and bisector, you can either say these 2 things are equal, or you could say equal halves, right? And I kind of told you before, the go-to should probably be equal halves, because it gives you equal if you need it, it gives you halves if you need it. With circles class, you almost always need halves. If you want to take a sneak peek over there at the board, do you see half, 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 half? Normally, you're going to want the halves when it comes to circles. But before we get too far, my reason class, definition of midpoint. All right, so there's our one clang.
This would be an easy proof though.
Now, the next thing, we want to look at what we're trying to prove. And I'm trying to prove something about a couple of angles. Within a circle, you ought to ask yourself, well, what kind of angles are we dealing with? Well, let's start with ABM. What kind of angle is ABM, class? It's an inscribed angle. It's formed by 2 chords with a vertex on a circle. What do I know about an inscribed angle, class? It equals half its arc. So I know, number 3, that angle ABM is equal to half of arc AM. Because an inscribed angle equals half its arc. Or if you want to sound really good, half its intercepted arc, but I'm lazy. An inscribed angle equals half its arc. We then turn our attention, we'll take the questions in a few minutes, to angle C. That's the other angle that we're trying to prove something about, right? What kind of angle is angle C? Also an inscribed angle. So what do I know about angle C then, Jamie?
That it equals half of arc AB.
Angle C equals half of arc AB. For the same reason, so that's also part of statement 3, because again, an inscribed angle equals half its arc. Now the question is, how to get ABM to be half of angle C? Chris?
Why not make A and B a triangle? No, I'm just kind of brainstorming.
So drawing the auxiliary line AM.
Yes.
Okay, thoughts?
Well, my thought here is, if ABM is half of AM, all we have to do is get the angle at B, and then we'll have our answer, right?
What do you mean get the angle at B?
Like, get the.
Or are you talking about this angle at B?
Like, well, if we get that's a half, right?
What's a half?
ABM is half of the, what angle would that be? Let's
Oh.
number some angles, let's number some angles.
Alright, so you're saying that 2 is half of the whole angle here? That is not correct. No, 2 is not half of the whole angle.
Why would it not be?
Why would it be? The burden of proof lies on you to say that it is special. I'm saying there's no reason to believe it is special. You're saying it is special. Why would you think it's special?
Well, that won't work either.
Yeah, no. The proof is much easier than that, actually. Let's look at what we just said. In statement number 3, looking at the bottom half there, we just said that angle C is what, class?
Half.
Half of what?
AB.
AB.
Algebra.
Angle C equals half of AB. I feel like earlier in the proof we said something else was half of AB. Not AM plus BM. AM and BM. Let me draw it a little bit more pronounced so it doesn't look too much like a plus sign. We just said AM's half of AB. We said BM's half of AB. Now we're saying C is half of AB. You know what that means? AM, BM, angle C, they're all equal to each other, right? Number 4, arc AM equals arc BM. We'd already kind of said that here. Equals angle C. They're all equal to each other because all of them are half of AB. Now again, we're referring to this equality between an arc and an angle based on their measure in degrees. An arc is not the same thing as an angle, but they can have the same degree measure, and that's true here. Reason?
Halves are equal.
Halves of?
Halves of a whole.
They're all halves of the same thing, right? They're all halves of AB, so we could say halves of equals are equal. For that matter, if you said substitution, I couldn't really knock you because they're all equal to what? Half AB. And since they're all equal to the same quantity, half AB, they're all equal to each other. So you could even take a substitution as well, or halves of equals are equal. Either one would work. Now, how does that help me to get ABM equal to half of angle C?
Because equal arcs means equal angles, right? In a circle.
What substitution, Jamie?
Put angle C like as angle ABM equals 1/2 of AM, and you can substitute the AM for angle C.
Yeah. We already said angle ABM was half of arc AM. And since we said that angle C is equal to arc AM, angle C can slide right in here where it says arc AM, and that gives us that angle ABM equals half of angle C. Substitution, and we're done in 5 steps. We've never done a proof quite like this before, with the substituting an angle in for an arc and things like that, but because of the relationship between arcs and angles, and halves and things of that nature, you'll be able to do this in circle proofs. Therefore, this angle, it's not necessarily half of the whole angle at B, but it is half of the whole angle at C. Questions on the proof? Extra credit this evening is not a proof, it's a math problem. So one of the easier extra credits I've assigned this year. For extra credit, page 152 at the top, number 5. Page 152 at the top, number 5. Your extra credit this evening. We'll take a look at that tomorrow. We'll also delve into what you copied into your notebooks for Theorem 43. We'll look at that tomorrow as well. Have a wonderful rest of your day, and you are dismissed.